All right, we're going to figure out how to determine net charge on a dipeptide. Net charge on dipeptide. So dipeptide just means two amino acids put together by a peptide bond. And let's do alanine aspartic acid. Okay, ALA-ASP dipeptide. So whenever, like I recommend, first thing, whenever you have to do this problem, draw the dipeptide in a fully protonated form. So I'm going to start for any dipeptide or tripeptide. You always start with amino acid, so amino group, right? Then we're going to have CH, that's your alpha carbon, and then C double bond O, right? And it's not a full carboxyl group because this carboxyl group is tied into the next amino acid by a peptide bond. So I'll make my peptide bond green. And so it's going to be NH, CH, C double bond O, right? And this one is our last amino acid, so carboxyl group, fully protonated OH, right? So green is aspartic acid. And so I'm going to fill this in. So it's CH2, C double bond O, OH, right? So we have another carboxyl group on aspartic. And then let me switch back to the purple. The alanine is just CH3, right? So I have two amino acids tied together. Notice that alanine by itself has two pKa's. It's 2.3 and 9.7 pKa's. Okay, 2.3 goes with carboxyl group, 9.7 with amino group. You can look them up in the pKa table. Aspartic acid, let's stick with the color scheme. So aspartic acid by itself is going to have 3 pKa's, and you can look them up in the table. 2.0 for the carboxyl, 10.0 for the amino, and then 3.9 pKa for side chain. So these are all pKa's. Okay, but when you have dipeptide, so as soon as you put this together into ALA-ASP dipeptide, aspartic acid, how many pKa's does dipeptide have, right? So this is dipeptide. Can you see that dipeptide will only have 3 pKa's? It's not 2 plus 3, it's just 3. So let's circle which pKa's, or highlight which pKa's does the dipeptide have. So you can see here from alanine, we keep amino group. So we need amino group pKa, right? And then what used to be carboxyl group and had pK is no longer ionizable because it's tied into a double bond that can no longer be ionized. Okay, then we still have side chain pK and carboxyl group pKa from aspartic. So I'm going to circle this one and carboxyl right here. Right, so the 3 pKa's at the left, actually I need this one, are going to be 9.7, 3.9, and 2.0. Not sure why I wrote them from large to small. That's just how I looked at them. Right? We can rewrite them in any order. All right. So then if we want to know net charge, oh, I didn't tell you at which pH. Let's pick a pH. How about at pH 3? Right, so say we would like to know this for at pH 3. So at pH 3, we're going to go around this molecule and compare pH to pKa to figure out if the proton is on or off. Right, so here's my pK 9.7. So at pH 3, pH is lower than pKa, 3 is less than pKa, right? So proton H plus is going to be on, right? Then at the next one, pKa equals 3.9, pH equals to 3. pH is, again, less than pKa. So when pH is lower than pKa, H plus is on, and the net charge is no charge, no charge. Whereas here, there was positive charge, +1. Yeah. And then for the last one, pK equals to 2.0, pH equals to 3. So when pH is greater than pKa, right, then proton H plus is off. And when proton is off in a carboxyl group, net charge is negative. So we have no charge, negative charge, and positive charge, right? So overall, net charge on the peptide is going to be 0 on the most abundant form, right? And we figure this out by kind of comparing pH to pKa of each group and figuring out if proton is on or off. Okay, so if this makes sense, you're going to say, wow, that's a lot of work, right? So I want to show you a shortcut, but I only want you to use it if you really understand like why we can use that. And also, if I ask you, can you please draw a dipeptide at a given pH? When you have to draw, I am expecting you to draw like all this, right? What I show you now is going to be a shortcut that doesn't show the whole structure. But if you need to draw the structure, this is what you're drawing. Oh, well, except I didn't. Let's fix it. So before I go on to the shortcut, let's fix this. So proton was on. So let's just take off the proton that needs to come off, right? So the correct structure would then have O minus right here. And then this would be the correct structure at pH 3. So just had to change one thing. All right, now the shortcut. All right, so you still start with fully protonated. And at fully protonated form, if you remember, it had net charge fully protonated, right? So that means all protons that could be attached are attached. So if you go back to your notes, you should see that the net charge on the fully protonated form was +1. Okay, so this form is +1, has 3 pKa, so I'm going to put 3 equilibrium arrows. And every time you have an equilibrium arrow, H plus comes off and takes positive charge with it. So this first pKa, let me switch color so it's a little more colorful. First pKa is going to be 2.0. Then the next pK is 3.9. The next one, 9.7, right? That's the last proton to come off when pH is above 9.7, right? And then we just mentally subtract positive charge every time we go across this arrow. So if I take one positive charge off, this will become net charge 0. Then it will become -1 and -2. Yeah. And so now with this shortcut, if I ask you what's the net charge on the most abundant form at pH 3, you're going to look at it and say, oh, 3 is between these two, so the net charge is 0. If I ask you what is it at pH 10, 10 is higher than 9.7, net charge is -2. Right? And if you think about the question that asks, well, what's the ratio of the two most abundant forms? You can use this model to help figure that out, because for each pKa, right, as long as you figure out which pH is closer, so if my goal is at pH equals to 10, right, what's HA, what's A minus, and what's their ratio? For pH equals to 10, let me switch color a little bit. So at pH 10, this would be HA, protonated form. This would be A minus, deprotonated form. And their ratio will be related through Henderson-Hasselbalch equation, where you can write pH equals pKa plus log of ratio, minus over HA, right? And just plug in if pH is 10, this 9.7, then the ratio A minus, let me scoot up a little bit, over HA is going to be 10 to 10 minus 9.7 raised to this power. Okay? And so you can figure that out. All right, hopefully You can practice with that and then do this independently. Okay, also keep in mind there's a really tricky amino acid, that's the histidine. On your amino acid sheet, it looks like the side chain is uncharged, right? But the side chain is drawn at pH 7 and pKa is 6. So that uncharged side chain is already deprotonated. So when you draw this protonated, you have to start with positively charged side chain. And so hopefully you'll practice in lab for that. All right, good luck.